Hi, I'm Mads Torgersen from the C# language design team. I'll take you through some of the features we've added in C# 7.0, the new version of C#. Let's start small. Here are some numbers. Just like we let you write numeric literals in decimal or hexadecimal notation, we now have binary literals. They look like this: 0b followed by the ones and zeros that make up your binary number. Literals often get long, especially binary literals, which is why we added digit separators in the form of underbars between digits. They can be used in any numeric literal, of course, not just binary. You can have as many as you want, but here, let's stick with a binary literal with just one separator. Now, let's talk about tuples, one of the major features of C# 7.0. Let's say we want to write a tally function to compute the sum and the count of the numbers we give it. We want it to have two results. Using tuples, you can declare tally like this. Look at the return type. It's a tuple type, with in this case two other types in parentheses. That can be more than two if you like. The type represents the value that holds two ints. Let's start with a dummy implementation of the method. Here I create a tuple value using a tuple literal. It consists of two zeros, again in parentheses, which we promptly return. In a little bit, we'll implement the method for real. For now, let's go back to the caller of tally and look at the different ways you can consume a tuple. All tuples have members named item 1, item 2, and so on that I can use here to get the sum and the count. You can always use these names to get at a tuple's elements, but they aren't very good names. How can the caller know which is the sum and which is the count? Let's give them better names. The tuple now declares names for its elements. The consumer can still use item 1 and item 2, but they can also use sum and count, the names we just declared. You can also add names to a tuple literal like this. As you can see with the literal, it's not a problem to return or otherwise assign a tuple with different names. Tuples mix just fine, regardless of the names, as long as the types match up. A third way to consume a tuple is to not even hold onto the tuple itself, as we do in T here, but to deconstruct it right away. What's going on here is that I declare two new variables, sum and count, and immediately split the tuple into its parts, assigning each to a variable. Now we can use those variables directly in subsequent code, as with sum and count here. Now, let's go implement this method for real. We need a for each loop to go through all our values, and each time around, we update the result tuple in R. I simply create a new tuple from the old one and reassign it into R. There's no need to be concerned that creating new tuples like this all the time costs a lot of allocation. Tuples are structs, that is value types, so they are created locally and are passed by copying the contents. Tuples are in fact mutable, and the elements are simply public mutable fields. So if I want, I can instead update R by first updating the S field and then incrementing the C field. So that's tuples. Now let's talk a bit about local functions. Say that I want to abstract out the way I add to R into an add method, but I want it to be able to modify R directly. I can now do that by declaring add inside of the tally method. This is called a local function. It has access to all the local variables of the enclosing scope, but can itself only be used inside the scope it is declared in. Finally, let's look at pattern matching. Patterns are a new kind of construct in C# that can be used to test values in various ways. Among other places, patterns can be used in is expressions. Here is the simplest possible pattern, a constant pattern, here using the constant value null. The is expression here simply tests whether the given value O is null. The type pattern is more interesting. Just like you're used to from the is expression, it checks to see if O is an int. But if it is, then the new variable I now holds that integer value. So in the subsequent code, since we can only get here if the is expression was true, we can use that integer value I directly. Patterns can also be used in switch statements, which have been greatly enhanced in C# 7.0. First, we can now switch on anything. The switch expression is no longer limited to primitive types and strings. And if we start from the bottom, we of course still have default sections and cases with constants, as with null here. But we've now generalized case clauses to hold patterns. So think of the null here as a constant pattern. That doesn't make any difference, of course, until we start using type patterns in case clauses. Here, we are now checking to see if the incoming shape is a circle, and if it is, we can call it C, and we can use it as a circle in the body of the case, getting at the circle-specific radius property, for instance. Now, we can do the same with rectangles, but we want to also add a special case for squares, which don't have their own type in this example, but are simply rectangles with equal sides. So here, the case clause has a when condition, further filtering the input that it triggers on. The when condition is just any Boolean expression, which is similar to the exception filters that we added in C# 6.0 to catch clauses. And similar to those, if you don't fulfill the extra conditions, you just fall through to the next case, the next rectangle case in this example. So that was a sampling of some of the new features to come in C# 7.0. There are more, and to learn more about them, go to my recent blog post, and of course, install Visual Studio 2017 and play with it. Have fun with C# 7.0, and thanks for watching.